So good evening everyone, I am Kalman Joseph and today I'm going to conduct the week 12 problem solving and clearing session for the course State Space Approach to Control System Analysis and Design taught by Professor A.P. Tiwari of IIT. Okay, so in this week, Sir has taught about periodic output feedback of control which was applied to a nuclear power plant, nuclear system. These nonlinear models are derived and which we derived in last class as well. And its linearized model and using that the cross controller was designed for the fast output sampling which was shown. And then why do we require a Kalman filter when we want to get, the measurement as a very slow response. The sensor is very slow. So to offset that, to overcome this problem of slow, sluggish uh, sensor response, how a Kalman filter was used, so as providing some basic in the show. Okay, so let us start. So we will do U12. Okay. So there are 3 points. One is the POF, periodic output feedback. Okay. Where and then we have fast output sampling, FOS. Fast output sampling. Then storage is the Kalman filter. So Kalman filter, as we remember, it will minimize square of the error and it has two stages. One is prediction and next is correction. It follows both these stages. Okay, it will first predict and then it will correct, right? And it is used mainly with service rule, lecture 88, where okay, it will minimize the mean of the squared error, right? There's certain noise, there's certain unmodeled dynamics which are present in the practical system and how it will minimize it. And then it will, you will see the vanadium SPND. Okay, they are used for providing high accurate measurement of the neutron flux density. Neutron flux density has to be measured. So this PT or COS and BDs, they are very fast. They can respond in a very fast manner. And so they are used for protection purpose. That is in case the flux density has increased a lot or the flux density has resulted very low. Okay, so they have rapid variation they can do in response to the new change in the neutron flux density. However, this vanadium SPND is a bit slower. Okay, it has high accuracy, but they respond slowly to variations in neutron flux. So now to improve the response characteristics of the vanadium SPNDs, what they do is they augment a Kalman filter. So the observations of the vanadium SPND from the sensors is provided, and then they add a Kalman filter to it. Right. So let us go to the first thing, lecture 26. This is periodic output feedback control. So Sir has taught linear output feedback control is designed for a nuclear reactor. That is just simple output feedback. We did not do state feedback. And now we will do design of periodic output feedback control will be considered. So these are the differential equations of the linearized model. So the actual plant is a nonlinear model. And then after certain perturbation and linearization, this is the differential equation of the linear model, which is shown over here. And then, so these linearized equations are arranged in the standard state space form. That is this, x of t is a of xt plus b of ut and y of t is c xt. So you can see this is a linear time invariant system. It looks like that. This is linearized equations form an LTI system, okay, where these are the states and these are the outputs. and the input is used with delta change in the input image. So these are the system input and output matrices which are given like this, and A, B, C matrices are provided. And in the last class, I had shown the controllability and observability of this linear model, solid flow. And we also had checked for various things how we cannot, if we use only output one, we still cannot observe all the states. If we use only output two, we still cannot observe all the states. But when we use the combination of output one and output two, then we can say that the system is observed. So that also we should. Okay. So now this is our fight, and this is gamma T. So how is this obtained? So in POM and FOS, these are digital control algorithms, right? So our original system is this are linearized system. X of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t. This is our system. Now, upon discretization, we have to do what is discretization. Then we get our x of n plus 1 is equal to phi n x of n plus gamma n u of n. Sorry, it is phi t plus gamma t u of n. Okay, and y of n plus y of n is c into x of n. Okay, so this is similarly shown over here. So now, what is phi t? Phi t is actually e raised to power a into t. And gamma t is actually integrated from 0 to t e raised to 8 tau d into u of t minus tau into d tau. Okay, so gamma t is actually equal to integration 0 to t e raised to 8 tau d into d tau. Okay, and that also I have done in my code. Where how did I compute? So this is omega t's integration of expression. Expression is a into tau into b integrated from 0 to t. And then I have found the gamma t, which is the actually the numerical expression. So this is the way. So gamma t is what? Integration 0 to t e raised to a tau b into d tau. Now there are another set of difference equations will be formed. We have to get there is concept there are n samples. Okay, n samples. This is taken depending on the observability index, controllability index, etc. All this is done. So the t nu is actually t by n. So we'll get a phi t nu and you will get a gamma t nu as well. Both of these will be found. Okay, both of these concepts will be used in periodic output feedback as well as in fast output sampling as well. Okay. So now, if you consider t equal to 1 second, then this discrete time system is given by this equation. So I will show you how it is coming. And the next one is denoted by phi delta and gamma delta. And this is the output injection gain, which was found. So let me show. So first, we will do the MATLAB demonstration. So let me run this section. Okay, so this is the A matrix, this is the B matrix, this is the C matrix. Okay, I've defined it and we have also verified it in last class. Okay, then these are the parameter values which we are knowing. They've been provided to us. We will run it and this we will get this overall A matrix, B matrix, and C matrix. Okay. After we get that, what we will do is our A num, B num, C num is the numeric values. Then we'll convert it into double. For they are still in symbolic, we convert it into double. Symbol. Then T equal to 1 is the sample time. As over here. T equal to 1 is shown. Then phi t is what double of this expm of A into T, and we are considering the sixth up to the sixth numeric value. Then this is for this is the expression which is there, and this is the integration of that expression. And this is how we get a gamma. Now, this is for del, where my del is equal to T by M. This is a phi del, and this is a gamma del we found. Okay. Now, this is where things have become very interesting is they have told us that you must place the poles over here at 0.9456 plus minus 3.3225 into 10 to the power minus 2 minus 0.50643 minus 0.12721 and 2.8176 into 10 to the power minus 9. So these are the poles. So if you'll observe all these poles, we see some poles have positive real part. This is sometimes confusing, but you must remember that this is a digital discrete time system. So in this case, we want all the poles to be located within the unit circle. So this is the first idea. Then for periodic output feedback design, the poles are placed at phi t plus GC. Okay, these are where we place the closed loop pole. So we'll consider phi t and C remains the same, and we have to select some G. So we can do place. We can place the poles phi t, and over here, what is the criteria is in of control closed loop eigenvalues are placed at using phi t plus g into c. This is where we want to place the poles. But in MATLAB, for place command, what do we use? A and B, consider u equal to minus kx, we get a close to is what? A minus b k. This is the equation. But if you want to do this is for state feedback design. State feedback design. If you want to do observer design, then we will use, that is, we want to get A minus LC, we use place A transpose comma C. A transpose comma C transpose and the poles location. In our case, we were doing phi t plus GC. So we must use a command place phi transpose, this is phi t. So we will use phi t transpose comma minus C transpose comma poles. This would be our command. So this is the slight variation which you have to consider when you're doing the design. So I've incorporated that. So we get G places place phi t transpose minus C transpose and the pole locations we put. And this is the G place we get. Okay, this is the place we get. When you do G place comes out to be minus 0.52089, 0.0142, 171.68, minus 7.461, etc. So these are the values of those gains. But over here, the gains are given to be this minus 2.2439 to 10 to the power minus 2, and minus 4.23327, but we are not getting that same value. So why is that? If you will remember, this becomes a multi-output system. So there is no unique solution. There is no unique solution. So I will show. If you will see, this is, let us open this. So if you will consider this eigenplace, eigen underscore place, you will find it to be at the same value, minus 0.50643, minus 0.1271, 2.8176 into 10 to the power minus 9, 0.9456 plus minus 0.03325 I. This is where we want the poles. But the gain matrix G place is different as to what Sir has shown. So then what I did, I put the gains which Sir has in his lecture. That is, this is the gains Sir has in his lecture. And then, if you can cross check, it is minus 2.2439 into 10 to the power minus 2, minus 0.027128, which is again shown. Then minus 4.237 and minus 0.51171, minus 0.20971, and so on. So I've used this G lecture as the gains which Sir has got. And now I am checking the eigenvalues for what Sir has considered. So let me run this section again. So when I run it, I'll get the same polarity, 0.9456 plus minus 0.03325J, then minus 0.50643, which is the same, then 2.8176 into 10 to the power minus 9, which is the same, and minus 0.1271. So there are multiple solutions for G. You'll observe there are multiple solutions for G, okay, which is surprising for us. Okay, it is surprising. Then we have to find gamma, and which is Sir is doing over here. So this gamma, this capital gamma, is a thick one. Capital gamma is equal to, if you look at the expression, it is phi del into gamma del. Okay. It is this gamma del, comma phi del into gamma del, comma phi del into gamma del, phi delta square into gamma del, comma phi delta cube into gamma del, comma phi delta raised to 4 into gamma del. Okay, so this is the gamma which we get, and our k is the inverse of this capital gamma into G, okay, which I have shown. So K place is inverse of gamma into G place, which I've got through pole placement using MATLAB's function, and with this K lecture is inverse of gamma into G lecture. So let us run. So we will see this is the K place, this is the K lecture. So there is a difference, and if you'll observe that the ones which I have got through MATLAB's pole placement, the gains are very high. They are very high, and this is not desirable. But in the ones which Sir has used, the gains are low. So the response will be a little bit better. So there are multiple solutions to G and K. So there is scope for optimization. Right? One can use LMI techniques, etc., for evaluating the best set of gains. Okay. One of the criteria is the gains K should be as small as possible. They shouldn't be very large. That is one of the criteria. Okay, so this is how we saw what is known as periodic output feedback. Now let us go for the let us see what for the short. Suresh, we can use alternative by selecting a higher number of values, etc. That is up to you. So this is the response which you can observe. Amplify POF gains K1 which are used. And this is the response when the gains are K2. So also Suresh shown. So it's up to us what value of n we take and what value of gains we consider. Let us go to the next lecture. This fast output sample. FOS. That is fast output sampling. So these are the differential equations of the linear model which we have considered. This is just shown. And again, we have the state space representation ABC matrices all over again. This we have already seen it. So now, what we do over here is they have told us to consider t equal to 0.25 seconds. So let us reevaluate it. So let us make a new section which is for dedicatedly for this text and this heading is fast sample. So we have already found out what is my A num, B num, C num. We have already found. Now we don't want to use these set of stuff. We'll comment it out. Now let us start. So they told t equal to 0.25 seconds. So t is the sampling time. The sampling. So t is 0.25 seconds. Next, we have to find phi of t. So phi of t is equal to expm a into t. Now this a will be a numeric into t. Let us run this. So this is phi t. It comes out to be in this expression. So if you see, because I'm using symbolic math toolbox, it comes out in this form. We can convert it into PPA 6. Let's try it. What is the actual value? It comes out to be in numeric format, but it will be best if it is converted to W. So W means it is easier for math to calculate. It will no longer consider it as a symbolic math toolbox variable, and so it looks like this. This is our phi t, which we got. So phi t has been obtained for t equal to 0.25. Now we do for Kalman. So the expression is expm. We take symbolic variable tau. The expression is what? expm a into tau into b. And we have to do omega underscore t. Omega underscore t is integration. See, here. integration of expression tau 0 to. So integration of expression tau 0 to t. So this is omega t. Let us check it. What we get it as omega underscore t comes out like this. And then we put gamma underscore t is again double of APA omega underscore p comma 4. So we run it, we'll get gamma underscore t to be this. So let us check it. So gamma t comes out to be 0.00386 minus and then 3.0864 to 10 to the power minus 2, 2.4307 to 10 to the power minus 3 minus 5.6775 to 10 to the power minus 3 and 1 into 10 to the power minus 3. And similarly, if we check phi t, there is 0.001 and then again 1.2 into 10 to the power minus 4, 0.39 etc. So we have got our phi t and our gamma t we have found, which we need. Let me count it because now we have checked and they are correct. Now C remains the same, C numeric. Now we have to go for delta. So del is equal to, so in this case, n is equal to what? So n is 5. So n is 5. So del is equal to t by 5. Okay. So my phi underscore del is given by this expression. We just copy this entire thing. So this is phi del a into numeric into del into 4. Then here this expression exp made into tau into b. Omega underscore del is expression tau 0 to not t in this case, it will be del. And gamma underscore del in this case will be double VPA omega underscore del comma 4. So let us check these expressions. What comes out to be phi del? So phi del is again 1.2306 and 10 to the power minus 4. Here also that same thing 0.38606 and 0.998, 0.99800, 12.114, which is again correct. Triple 4 zeros at bottom and then 1. So it is correct. And gamma del comes out to be 7.4962 into 10 to the power minus 5, 1.1753 into 10 to the power minus 3, 1.155 into 10 to the power minus 4, minus 6.4736 into 10 to the power minus 5, 2 into 10 to the power minus 4. So this was what we got gamma del. Okay. So we have checked both are coming the same. Now let us consider f. That is the state feedback in f is given by this formula. So let us say f is equal to minus 894,894.3956, then 0.1760, 0.1760, then minus 69.1711, then minus 0.0236, 0.0236, then 484, 484.225. 484.225. So let this be my f. We'll run it. This is f. And what are the eigenvalues of phi underscore t plus f gamma t into, so what is gamma underscore t into f. Let us run this. So these are the eigenvalues. It is 0.001, 0.2, 0.85, 0.9, and 0.99. Okay, so these are eigen underscore lecture. This is f underscore lecture. Let us try placing our own. So the poles which we wanted are, so this we don't need. This is correct. This also is correct. We don't need. The poles we wanted to place it at 0.001, 0.001, then 0.2, 0.2, then 0.85, 0.85, 0.9, 0.9, and 0.99. This is where we want to place the poles, and we will do f underscore place is equal to place of phi underscore t transpose comma minus gamma underscore t transpose comma. So this is our f which we want. F place, let us run it. We is the problem gamma t into f plus b. We derive it here. Here we place a force phi t plus gamma t into f. Gamma t into f. So this is similar to a plus b k. No, the place does a minus b. So this would be phi. So what we should do, the place will do a minus bk. So we must use at one place phi t comma minus of gamma t comma poles. Okay, let us say the place of phi t minus gamma t and the poles. So let us check what f we get. So we get f place, we get f place to be like this. Then we'll see what is the eigenvalues we get from pole placement. So the eigenvalues by place, if these things are not required, we'll comment it out. Place is equal to eigenvalues of phi t plus gamma underscore t into f underscore place. Okay, let us see what are the eigenvalues of place. So if you see eigenvalues of place of 0.01, 0.2, 0.99, 0.85, 0.9. So they are similar. So eigenvalues of place and eigenvalues of lecture are almost same. So hence also there is no unique solution for f. Multiple solutions exist for the same pole locations. Okay, so this has been proved. Now we will check. We have to find C. Now C is given by C into phi delta, C phi delta squared dot over C into phi delta into M. Okay, so that is this numeric thing. Let us go for this. So we'll use the same code. This C naught. So what is this? C underscore naught. It goes from, okay, let us do one by one. So it will have C into phi delta. So C into phi underscore delta. What does this come out to be? So C into phi delta. Then it will have C into phi delta into phi delta. Okay. So this again comes out like this. Okay, which is also quite similar to what is a video. So that means we have to just incrementally add it. Okay. So here, for I going from 0 to 1 to it is going from 1 to n. just step size. So our C naught is equal to C naught. Then next row, so it will be C into phi underscore del raised to I. Let's check this what it comes out. We will see this is our C naught. Let's take the first column 0.9095 to 4.6155, 0.0582, 2.677, 0.0358, 1.5043, 0.022, 0.796, 0.014, and 0.362. Okay, it is something similar. So our C naught also is correct. So we have got a C naught. So this is for compute C naught. So now once we have got C naught, what do we have to do? We have to find D. Okay, so D is a little bit more complicated. It is C into phi delta and C phi delta plus C phi delta into gamma. So C is common summation of j equals 0 to n minus 1 phi delta transpose into gamma. Okay, so let's go to the calculate, right? So that is C into phi delta. What is it? So C into phi delta is given by this expression. No, this is not C into phi delta, this is C into gamma delta. Gamma delta. So C into gamma del is 0.00155, 0.00768. Okay. Then we have C into gamma del, C phi del into gamma del plus phi del. Okay. So it is C into phi underscore del plus gamma underscore del. And this also into gamma underscore del. So this comes out to be 0.000005 52645 0.02715. Okay, similar. Then this will be C into phi delta into gamma del plus again phi delta into phi underscore del into gamma. So that comes out to be 0.001089, 0.0010989, and 0.0534. Okay, so this comes out to be like this. So our actual expression is gamma del phi delta into gamma del plus gamma del. So it is summation of I. So first is I is 0, then I 4. So that is 2. D is first into I is going from 1 to 1 to n. Okay, and it is ending. So let us say I is going from 0 to 1 to n. It is going to n minus 1. Okay, n minus 1. Then our D is equal to D. Then it is going as uh, C into C into gamma del. Gamma del, but we have to do the sum of it. So we have to have a summing function as well. Mhm. Please declare variable sum. Sum is what? Equal to I. Sum is equal to, let's say a temporary variable that is equal to slice of 0, sum is equal to sum plus I underscore del is to the is gamma underscore del to I into j into it is actually phi del. Okay. Phi underscore del j into gamma underscore del. So let us just check that is 4 from 0 to 1. That's right. Mm, Some comes out to be like this. Please consider this thing. Here is going from 0 to I. Let us say I is equal to 1. Okay. Or let's say I is equal to 0. If I equal to 0, then what will this one need to be? Please evaluate it. So output sum is equal to 0. Then this section, sum comes out to be like this. Why is it coming like this? So what is the value of j? 0. Power of phi del is power of phi del over 0. This is power of phi underscore del about 2. What is phi underscore del into phi underscore del? It is different. Okay, that is not permissible. So how should I do power for matrix multiplication? Okay, Power is what? M power is matrix model here. So let us do M power in 5 square del command one is this. 5 square del square is this. 5 underscore del into 5 underscore del is again this. So we have to use M power. Okay. Let us say I use M. So let me see this. So what is M power 5 del with J into gamma? So this is 1. So then sum, let us run this section. So this I get sum. So I've got sum. Now after sum, what has to be done with sum? Sum actually is just this 5 del 5. Okay, so it has to be multiplied with C. So you know C into sum. Okay, that comes out to be this value. Okay, let me run this now. Let us say I is 1. With 0.0155, 0.07865. So which is here 0.001520, 0.0048. Okay, 0.00052 and 0.027. Okay, it is matching. So now I equal to not 1. So I equal to 0 to 1 to n, which is going to n minus 1. Okay, n minus 1. This ends over here. We get d is equal to this. Okay, let us run this now. So d is equal to this. We run this section. We get this d. So d is 0.00155, 0.007685, 0.000. J is going to be 0 to 1 to I. So it goes 0 to 1 to I. So let us run it again. Some mistake. The error. D is empty. This n is fine. Let's pause it over here. So breakpoint. Let's run this section. So at this time, what is my D? D is this, and what is my sum? Sum is this. So C into sum comes out to be like this. Okay. Let us continue. Please let run next line. And what is my D? Incident of running. Stop. Let me run this section. So D now is like this, sum is like this. C into sum is done by this. Let me step over this. So what is my D? It's like this. Now I go over here and sum is this. Let me step over it. So sum becomes equal to 0. What is my I is 1 and j is 0. Let me step over this. J is still 0. So what is this? Copy this m power 5 del. This actually is equal to gamma delta. This is gamma. Okay. Now, so let me step over this. What is my sum now? What is my sum? Then let me again step over here. This is still my sum. Let me again iterate. So now what is the effective sum? This is my effective sum. Okay. Now D should be D into C into sum. That is the issue. Let me disable this breakpoint. Let me run this section. So we get it 0.00155, 0.007685, 0.00055, 0.02715, 0.0010989, 0.053465. Okay, so it is approximately this, and D is given by this value. So we are getting approximately D is correct. So we have found the expression of D also. We have computed D. We just delete this. So we have found out D. This also we don't need anymore. We have found it using a recursive function or algorithm, etc. So we have got our D also, we have got our C naught also. Now what do we need to find? Capital C is C naught plus DF and phi t plus gamma TF inverse. Okay. So we get C cap. Okay, let me just use C cap because we already have C numerator. C cap is what equal to C naught plus D into F, D into F lecture. Let us do F lecture. So let us have C cap lecture. So C cap lecture C naught plus D into F lecture into phi t plus gamma t. So inverse of phi t plus gamma t into F lecture. So let us see what is our C cap lecture coming out to be. So C cap lecture is minus 2904.4. Okay, minus it is 0.3496. Yes, 7.3891 and so on. Okay, 50 and 1 is there. It is correct. So this is our C cap lecture. 7.96780 to 10 to the power minus 7. Okay, this is not correct. Minus 2.0153 to 10 to the power minus 9. There is some mistake. There's certain deviation. So what could be the cause? First of all, D, we were getting some value which is slightly different from there. So D will go round. D come out. So what is this also to be? 0.002, 0.0077, 0.006, 0.0272. What does he get? This is the one. Let us change degrees. Round off D of 4. Let us run this section now. So now minus 2923.4. 0.35194. This 2.365 10 to the power. This 50 and 1 is coming. This is not coming. There's some issue. What is our phi t? Phi underscore t. What is his phi t? Phi t This is 1.2366 into 10 to the power minus 4.0012. Okay, 0.39221. 0.998, 0.998, 62.108, 1.013952, 0.00128, 8.00820850, 3.5733. Okay, minus 14.4821, 0.88250, minus 2.10630, minus 0.00459810, minus 0.328370. So these are the same. So phi t is same. Let us check which is else is different. Let us see what is gamma t. Gamma underscore t is 0.00386. Okay, 0.0308644. 0.00243087 minus 0.0056775, 0.001. Okay, this also is correct. What is our C is also correct. And where is the blender starting? Okay. Now, if lecture you put eigenlectures fine. C naught, let us check C naught. So what is our C naught? This is our C naught. What is his C naught? This C naught is 0.0952. We have 0.095231, then 0.0047255. Okay. What do I do? Round off C naught, comma, 3 or 4. Where is the 4? Okay. It is 0.60650, 1.4798, 73.03, 2.4199, 117.6. Okay, there's still some numeric mismatch, 2.9961. Okay, let us do C naught, BPA, C naught, 4. Okay. Some cases it is 1.47. Okay. C naught, 6.4798. C naught, 5. So this 0.0952, 1.4798, 73.03, 164.18. If there is some mismatch, so let us do round of C naught, 5. C naught is round of C naught, 5. And D is round of D, 4. Let us now check whether it matches now. Run it. Still there's mismatch. So 50 and 1 is coming 0.00. There is certain somewhere we are making a mistake. But able to identify. Okay. C is C naught plus D into F lecture, phi t plus gamma t into F lecture. Okay. C naught plus D. Let us do C cap place. What we have got is C naught plus D into F underscore place into inverse of phi underscore t plus gamma underscore t into F underscore place. Let us check what this comes out to be. So C cap place again comes out to be quite similar. It also comes out to be quite similar. C cap place comes out to be similar. Then we have to solve for LC equal to F. So to do LC, what is our L? LC equal to F. Okay. for LC is equal to F, right? So we have to find the pseudo inverse. So L inverse, we'll see whether pseudo inverse is possible. We'll find the nearly similar P inverse. Okay, find the least square. We have to find the pseudo inverse of it. So L lecture is equal to F upon C. Underscore cap underscore lecture. Let us check whether it runs it. Okay, this is F underscore lecture. We'll run it. So L comes out to be 0 minus 8.0099. This is the L lecture which we get, but I have a feeling you have to use pseudo inverse and you are not able to do that. And L comes out to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this is 0 minus 8.099, 0, 0, 0. Okay. Let's check pseudo inverse. Okay. P inverse. Let's try. We have LC into F. So L is P inverse C into F. Let us check this. P inverse into F. So let us see what is L. What is P inverse C cap lecture? So we do still common. Size of F lecture 1 to 5. Okay, that is the transpose of this. We get minus 2418306. There is an issue which we have to check. We have to see what has caused this issue. Let us do it. So lecture into P inverse C underscore cap underscore lecture. Is on it. Coming out to be similar. We'll have to observe. We'll have to check why this is not matching, but there should be some particular reason which I'm currently missing, but I will further debug and check. So C cap lecture actually is very different. So probably because of that, our L lecture also is varying. It's quite different from what they have got. So this was for fast output sampling. Just hope you have seen the methodology which I have followed and you'll be able to use it. Now let us go for the Kalman filter. So this is the actual process model. There's a measurement part, and this is our actual discrete time Kalman filter, which is being implemented digitally, discretely in our processor, etc. So there's a system model which we have. Reactor variations are like this, and this is a neutron flux variation based on SPND signal. Okay, this is a Kalman filter equations. Let us check. So these are Kalman filter equations. Okay, so this is our phi t. This is a gamma t. Here u will be there. Pk is phi k, k minus 1 pk plus 1 phi k, k minus 1 transpose plus qk. And then this is the Kalman gain which has to be used. And this is the connected state covariance matrix pk. And this is the connected state xk. And okay. So this is the equation which was considered. What is xk? Is the output. Which is the output. So in previous classes, what have we done? Then we discuss about Kalman filter. Okay. There's the Kalman filter gains. And this is the methodology. So this you can Kalman filter. So xn plus 1 half, we will find xn cap plus gamma into given prediction step. And there's a predicted covariance methods. P to the n plus 1 is 5 into E n hat to the final transpose plus Vn. Then k n plus 1 hat tilde is the gain, which you have to consider, that is P n plus 1 tilde into C n plus 1 transpose, which let us check like this equation. So that is P n plus 1 hat is equal to I minus k minus k n plus 1 tilde into C n plus 1, okay, into P n plus 1 hat, okay. This is also fine. So what is the corrected state? X n plus 1 hat is equal to x n plus 1 tilde plus k tilde n plus 1 into y minus c n plus 1 into x tilde n plus 1. This is a predicted order. So this is the way the Kalman filter operates digitally in a discrete system. So what would be, we have to get phi n and gamma. What we don't know is this R, the R matrix. We don't know Wn plus 1 and this Vn. These two variables we don't know. So these variables, how are they found is we actually run our system, and then based on the output of the system, we will apply the Kalman filter to that data which we have obtained from the offline data which we have collected. And then we run this Kalman filter for different values of omega n plus 1 and Vn. And when we will run it for different values of omega n plus 1 and Vn, then we will find certain values which closely match the responses. Then we will choose those values of omega n plus 1 and Vn. So those are certain degrees of freedom which we have to control, to bring certain changes in our estimation to improve the accuracy of our Kalman filter or the speed of our Kalman filter, etc. Okay. So this is how the Kalman filter works, and this was taught over here. This is the corrected state. So Q and R should be chosen so that we will get the desired transient performance of the filter. And that was done by Sir, in which Sir has checked that this is the neutron flux variation based on this SPND signal, and this is the actual neutron flux variation. So there is a huge drastic difference, and this is because of the slow time constant of our sensor. So he has changed Q and he has seen that this is the output, but it is not closely matching, and this is the error which is there. Then what Sir has done, he has changed the value of Q and error has reduced. And at certain values of Q, the error is very, very uniform. So it's like white Gaussian noise is the value of Q. Again, these other changes. So R has been kept fixed and Q has been increased. And as we are increasing Q, you can see that the noise also is increasing. Okay, so there is a certain fine spot at which we can get a minimum value of our covariance, which we can select. Okay, so covariance can be efficiently used for tuning of Kalman filter parameters, and Kalman filtering application is an important area. It has been demonstrated by Sir. If this was done, let us check. So what we can do is we can have a certain recap of the course. So tomorrow I will be having my summary session of the course. So I will be teaching about various things. So let us go through my notes which I've taken, and we will see how to understand. So let us go. I have my drive. Better to get to my folder. Let us see one by one. Week 0 we will consider. Week 1. So week 1, state-space representation of a system, nonlinear system, linearity around the operating point, SISO system, mathematical modeling has been done. Okay. Right. Then MATLAB demonstration, op-amp system also has been shown. Derivation of transfer function, open tank system, continuously stirred tank, various difficult systems are done. So let us say in week 1, we have done the mathematical modeling of the system. So mathematical modeling of continuous time system. So there is the series RLC, op-amps, op-amp based filter, etc. So here you must know, okay, you can represent it as x dot of t is a into x of t plus b into u of t, and y of t is p into x of t. So this is known as state space representation. Okay, so this was taught in week 1. Right, let us go to week 2. Week 2. Week 2. Okay, week 2 has the state space representation. And that state space representation will be different for different states. But the transfer function remains the same. There's the first canonical form, second canonical form, Jordan form, transformation matrix. Okay. Then Laplace transform has also been touched. How to find the inverse? What is the characteristic polynomial of the system? First canonical system form, how do you find? Second canonical form, how do you find? Right? Jordan form, which has been shown. And conversion of state space form. How do you convert from one state space form to another state space form and converting into diagonal form? Okay, these have been taught. So week 2 has many things. It has what is known as the state space representation of a system. It also has transfer function to state space and state space to transfer function, both. Both are there. Then various canonical forms. So we have what is known as the first canonical form. Then there is the second canonical form. We have the Jordan form, etc. Then how do we transform from one state space representation to another form? Okay, so all these has been taught in week 2. So these are certain, important fundamental things which are easy to remember and which you can easily use. Like, you cannot find the periodic output feedback gain and etc. for this gamma del, phi del. It is very difficult for you to do. But if you should know the steps, like what is the methodology, etc. But these are simpler stuff. So these are more intuitive, more easy to understand. So this is week 2. Now we'll consider what was done in week 3. So week 3, is state space solution. The state transition matrix has been shown. How do we find the state transition matrix? Best ways, which I recommend, is using the Laplace transform, inverse Laplace transform. What are the properties of the state transition matrix? How do we use those properties to solve questions? What is an autonomous system? How do you find the eigenvalues, eigenvectors? Okay, Laplace transform. Okay, zero order rule for discretization, and etc. Okay, linear time varying systems. How do we tackle linear time varying systems? Okay. Mhm. Week 3, we considered what is the state transition matrix. The state transition matrix STM, then the properties of the state transition matrix. Further, we have seen uh, discretization of the system. There are two ways. One is using zero order hold, and one is using Euler's approximation. Okay, as well as we have also seen it for linear time varying system also. Okay, Laplace transform, STM. How do you find the state transition matrix using Laplace transform? This is my recommended method. But you get a closed form solution, as well as STM for linear time varying systems. Okay, this is for week 3. So these are the first 3 weeks. Now let us go for week 4. So in week 4, we have considered what is known as controllability. What is the controllability matrix? Controllability subspace, uncontrollability subspace, the rank, okay, stabilizability, detectability, observability, detectability, Jordan form, eigenvalues, eigenvectors, okay, cloud form. And now when we convert it into a Jordan diagonal form, it enables us to check whether the system is controllable or not controllable. Like helps us to see for different values of eigenvalues and eigenvectors. So week 4 is related to controllability and observability. Controllability and observability, as well as what is the matrix. The controllability is found using matrix Q and observability is matrix P. So these depend on A, B, and C. Then there are certain things known as stabilizability and detectability, as well as we can uh, do state space transformation, where there are certain canonical forms which are easier for us to evaluate controllability or observability. Controllability and observability. This is what was done in week 4. What is the controllability subspace, observability subspace, etc. we have seen. Now, let us go to week 5. Go to week 5. In the week 5, certain mathematical properties were taught by Sir. What is a positive definite function? What is a negative definite function? Then what is semi-definite, positive semi-definite? How do we represent a function, positive definite function in terms of a matrix, matrix representation, quadratic expression, how do we represent it? Then the concept of a surface. Then what is the concept of stability, boundary input, boundary output, impulse response, Lagrange stability, etc. Okay. Lagrange stability is based on the concept of energy. And we need to find a suitable Lagrange function to determine stability. There is a way to find A transpose P R plus R way to find this Q. It comes to be positive definite. Now for a nonlinear system, for autonomous and non-autonomous system, how do we find stability of waves, stability parts, then reverse stability for discrete system, which was shown. How do we determine reverse stability? So week 5 is related to stability. There are various ways. One is reverse stability, one is Lagrange stability. And to find Lagrange stability, we need certain mathematical preliminaries. Lagrange stability is related to the function of energy, and we need what is known as a quadratic expression. We need to know what is a positive definite function, semi-definite. How do you decompose a quadratic expression, etc. So these are the mathematical rules. What is a continuous surface? And how if a trajectory starts with no surface, whether it is bounded within that surface, that is they get to Laplace stability. How do we prove Laplace stability? There are ways to prove Laplace stability. Then how do we do for a non-linear path? How do we decompose it? And then for discrete time system. Because all these were taught over here in week 5. Now let us go to week 6. Okay, so this LK system for eigenvalue unstable. Okay, what is the concept of state feedback? And for state feedback, where we can place the points. Okay, this is shown. This Kalman formula is there. Bosco algorithm is there. Pole placement is there. Okay. Week 6. Week 6 is related to state feedback. We have a system A, comma B. We design a controller U to minus kx, which means we need to have a feedback with the states, and the overall closed loop transfer function is system matrix A minus bk. Okay, so that's like kind of like an autonomous system, and then we can do arbitrary pole placement is sort of possible using state feedback, as well as okay, there is formula known as Ackermann formula is there. And there is a Bhaskara algorithm also is there. But I recommend to go through this way. You find the A minus bk, very close to it. You find the inverse, you find what is the, you have, how do you, there's a poles. You have a desired characteristic equation. And you have an evaluated characteristic equation. And then what do? You do a comparison. Comparison of the coefficients. Or you equate the coefficients. Equate the coefficients. So this is week 6. There's for a discrete time system. If you want to do what is known as deadbeat control, what you have to do, you have to place poles in the origin. This for week 6. Okay. So it's a lot. I'll admit it's a whole lot of stuff which has to be done. Then we will go to week 7. Week 7 is about the linear quadratic regulator state feedback. How do we know where to place the poles? If we have so many criteria, then we can use LQR to place the poles. Then control input is limited, it cannot be infinite. Cost function optimization, we optimize a certain cost function. There's a weighting factor for the states, there's a weighting factor for the control input. Q should be positive semi-definite, R should be positive definite. This is doing mathematical analysis, which finally ends up in an algebraic Riccati equation. It is A transpose P plus PA minus PB R inverse B transpose P plus Q equal to 0. Then we find P, then we get K equal to R inverse B transpose P. Remember the P is a positive definite function, so it must be symmetric. LQR is valid even for systems which are multiple. Okay. So you get an algebraic Riccati equation and you have to solve it. Okay. Then we select R, we select Q. Okay. Week 7, which is LQR, linear quadratic regulator. Here we have to minimize the cost function minus infinity to infinity x transpose qx plus u transpose ru into dt. Q is positive semi-definite and R should be positive definite. Okay. And you get an algebraic Riccati equation, ARE, that is A transpose P plus PA minus PB R inverse B transpose P plus Q is equal to the O n cross n matrix. And the P is a symmetric, it is symmetric, that should be remembered, positive, semi positive definite matrix. Okay. Once we solve P, we get K equal to R inverse B transpose P. So these are important equations which you must remember. These are very much required for you. And this is what LQR is all about. We have to select some P, we have to select some Q, it might be provided, and you can find using the AR algebraic Riccati equation. So this is week 7. Now let us go to week 8. So week 8 is about observer. Now, if you want to do state feedback, we need to have the information of all the states. But in some cases and most cases, we cannot get the input, we cannot sense all the states. So in that case, we use an observer. So state feedback is a control law. Then the load observer is there, which minimizes the error. It just minimizes the error. The Kalman filter minimizes the square of the error. We have observer dynamical system, and there should be sufficient time scale separation should be present. And error dynamics appears as an autonomous system. Okay. And then to estimate the value of your state. We can use the Ackermann-Bosco algorithm also to find the value of our states. Okay. We can design an observer. So we have what is week 8. Week 8 is related to observers. So for state feedback, we need to measure all the states. It is not practically feasible. We cannot have u to the minus k. So what we do, we use an observer. An observer, what it does, it estimates the states. Then we can have a controller u to the minus k into x estimate. So when you use what is known as a Leuenberger observer, is usually what is one simplest observer which is there. and this minimizes the error P of t. Okay, and there should be sufficient time scale separation between um, system dynamics and observers error dynamics. Okay. And further, we place the poles at A minus LC. So these are the poles of the observer. All right. So we can again use the same Ackermann formula and Busbar algorithm can be used. Only we have to use instead A transpose C transpose poles and L is equal to place of that. Okay, so this is the way we can do for pole placement for observers. Okay, next we will go to week 9. Okay, week 9 starts with digital control. What is the difference between control time system and what is a discrete time system? Relay difference equations, what how the pole locations differ, what is the concept of stability for digital system, what is an ABC conversion to digital, how do you find the change and the states, IT, how do you can mathematically evaluate it as well, and then gamma also how it is found. Okay. You can find observability, the samples of the various outputs, multi-rate output controller, FOS fast output sampling. Where here observability index is important, P of is periodic output feedback, but here there's a discrete discontinuous approach. And these are advanced and computationally intensive. Contributing index also is an important factor. So week 9 is basically regarding this. Week 10 is regarding Kalman filters. Week 11 is related to the case study for nuclear power plant. So then we go to week 9, which is related to digital control. So then we have concept of Z instead of S. Okay. This for discrete time system, this for continuous time systems. Then the poles, they should lie within this unit circle. While in this case, sigma j omega, the pole should lie here. Here the pole should lie within the unit circle. Okay. Then there are three types of control which are taught. That is, one is MROC, multi-rate output control, where the outputs are sampled at different rates. Next is FOS. That is, the outputs are sampled at the same rate, fast output sampling. And this is POM, periodic output feedback. So these both are related to the observability index, and this is related to the controllability index. Okay. And this gives discrete discontinuous inputs. Fast output sampling is a this is a subset. Fast output sampling is a subset of multi-rate output control. Okay, so these are various different advanced control techniques. In fast output sampling, we cannot place the pole at the origin. There are certain other constraints which are there. Okay, so based on our requirements, and we can do the simulations for various control techniques, and we can decide which is best for us. Okay, so when we do multi-rate output control, feedback, fast output sampling, there's an important term known as observability index, which we have to make sure that the number of samples are more than that. So we have to first do that. Secondly, we have to also check uh, that we can do arbitrary pole placement. So there is no requirement for us to, to design an observer in this case. Here we are using the estimates of, we are sampling the outputs, we are sampling the inputs, and then we are able to do pole placement, which we can do through state feedback. But then state feedback was not always possible, so we had to use an observer to be able to implement state feedback design. But now with the advance of various digital control processors, which are very advanced, which are very powerful, and which are very cheap, etc., we can go for these advanced control techniques. That is MROC, FOS, and POF. Okay? So this is for week 9. Then we will go to week 10. So once we get these discrete time matrices, also we should always check for controllability and observability. That should be done. Week 10 is related to Kalman filters. So Kalman filters basically reduces the mean square error. That is its job. There are two types there, continuous time Kalman filter and discrete time Kalman filter. And again, over here, continuous time, we get some differential Riccati equation. Discrete time, there's a certain recursive algorithm we get. For discrete time, we have a certain recursive algorithm. Okay. So that is shown in this week 10 notes. So there is, in a practical system, we have noise, you have unmodeled dynamics. And now in the face of all these non-idealities, how important it is to have a stable system and we want to have a good response, then this Kalman filter, which is proposed by the scientist Kalman, has found various wide range of applications in various fields, right? So we can find closed loop stability also can be found. Distributed Kalman filter, the steps, the algorithm was shown, how we have a prediction step, they separated covariance matrix, then we find a gain, then we do the correction and update, and we update the covariance matrix, etc. So this is a recursive algorithm. And it has two steps. It has first is prediction, and then we correct our prediction. So this is the power. So this is the logic of the Kalman filter. And this very simple basic logic is used in various places. Okay. Done. So it has two steps. It has a prediction, and then it is followed by a correction. And then you have certain covariance matrix, and you have a Kalman gain K. All these are present, right? So next is week 11, where Sir has considered a case study of a nuclear power plant. So Sir has elaborated various details about the nuclear power plants in India, how they are used for research, they are used for production of electricity, how the number of them, how many are commissioned, some are decommissioned. the various types, heavy water based or normal water based, how the everything lengths are there, what control rods are used, what materials are used for fission reactions, etc. And what is the number of neutrons, around 2 to 3 neutrons, and how much of energy 200 mega electron volt is disintegrated when is generated when this nuclear fission. Now it should be a controlled nuclear fission. So develop what is the non-linear model, non-linear mathematical model of the nuclear power plant. Then Sir has found the linearized model around the operating point. Then what was done was controllability test and observability test was carried out. Further, after that, we have found what is known as the then output feedback based design was also carried out. Okay, and the response also was shown. Now, week 12, that is this final week for which the session was there conducted, consists of applying POF control, periodic output feedback control, and fast output sampling control. And to use a Kalman filter is applied to overcome the noise as well as the slow speed, sluggish response of our uh, sensor. That means sensors, slow speed of response. So POF is periodic output feedback, FOS is fast output sampling, and POF has discrete discontinuous jumps in input. So it is not popular for that case. Fast output sampling also is used, and preferably fast output sampling gives a better response than periodic output feedback control according to Sir. And also let's use a Kalman filter to help to estimate a neutron flux density, right? To get an accurate estimate and a fast estimate. Because if we don't have a proper and accurate and a fast estimate, then our control itself will be wrong, it will not be accurate. Okay, so that's what Sir has shown for Kalman filter. So basically the power of the Kalman filter is we have a low bandwidth sensor, but we are able to get a high quality, accurate information using the Kalman filter. Okay, so let me do a recap of the session. First, week 12, Sir has taught POF, FOS, and Kalman filter. At least these basic names, you have a periodic output feedback in which the output state is fed with different gains at different time instants are used. FOS is fast output sampling where we sample the output multiple times in an instant when we sample the input only one time. Kalman filter is used to minimize the square of the error. It contributes to prediction and correction. Okay, how do we convert a continuous time system to a discrete time system, which is very important. Okay, so continuous time to discrete time, we use phi of t is equal to e to the power 8t. So how do we get it? How do we evaluate? So this is actually the Laplace inverse of Si minus A inverse. Or that is the Laplace inverse of 1 upon Si minus A. So this is your numerical method or the calculation method. If as in the exam, you will not have any software. You will not have MATLAB to save you. You have to do it. Now, gamma t is integration 0 to t e raised to a tau B into D term, right? So it will be e to power A tau 1A into tau A into B, varying from 0 to T. So this is equal to e to power A T minus I into B into A inverse. Let us check where A inverse will come. So the confusion is where? Will it be A inverse e to power A T minus I into B, or will it be e to power A T minus I into A inverse into B? Which is the question. So let us check solution. I think it will be 6. We checked it. So just into week 5. Okay. And here also. Check. But I'll get back to you of how do we do. We like how do we do find this value, whether it is e to power at minus I into A inverse into B, or e to A inverse into A tau T minus I into B. So we can check on MATLAB now. So we have APN. We have what is our 5. This is actually a gamma T. This is our gamma T. This actually is EHPN A into T. Let's see what is A. So EXPN A into T minus E by E of 5 into inverse of A into B. Why is it not happening? What is inverse of A? J A not happening. Okay, because A has is not invertible in this case, but let us consider normal case of the heading CT to DT, where we have A is equal to 1 to 0 3. This will be this 1 0. Okay, 5 underscore T is EXPM A. Let us take T equal to 1. This is EXPM A into T. These are 5 of T. What is our gamma underscore T is EXPM of A into T inverse of A into EXPM of A T minus E by E2 into B. So this comes out to be our gamma T. Better let us evaluate this here. This comes out to be our gamma t comes out to be like this. Okay. Let me go top. That's why just sure. So let us find gamma t using this method. Here gamma t comes out again to be like this. So this is the correct one. But what is let us do the experiment t into inverse of a into b. This also is giving the same answer. This may be probably because in this case it is commutative, but in all cases it is not commutative. So we'll have to just check the accurate formula for this. Okay, so first recap. Today we have seen what Sir has taught in this week 12 of FOS Kalman filter. What is discretization, how it is done, how there are n samples for one output sample or one input sample, depending on whether it is for FOS control, how the closed eigenvalues are placed, and how we have to change the place function, the syntax to do pole placement for POF control. This is the value, how do we got a recursive expression so that we could do it back. And then how there are multiple solutions of G and K are possible. And we can also use LMI techniques further. This is further scope for research. Then fast output sampling also we have done. There is certain issue in the code, but we have to resolve it. Then there's a summary session for the course, which will be done tomorrow. And we just did a brief, what was taught in week one, what was taught in week two, what was taught in week three, week four, week five, week six, week seven, week eight. How it's just taught various things, the state space, transfer function, observer, state feedback, Kalman filter, digital control, periodic output feedback control, fast output sampling, and the application of Kalman filter, various continuous time state and Kalman filter, and various things are taught. So all the best for your. Okay, thank you. I'll end this session.